Welcome everyone to the series of webinars within the IMPACTIVE project, which, as you may already know, if you're here, if you're following us, it's a project funded by the European Commission to make greener pharmaceuticals. And the consortium is trying to do that using a technique called mechanochemistry, which basically uses mechanical force to mix and mash molecules together and come up with greener ways to make pharmaceuticals without using solvents, which is more sustainable and hopefully will reduce the environmental impact of the pharmaceutical industry. We have organized a series of webinars during the duration of the project, which is coming to an end later this year. But today it's a huge pleasure to have with us Professor Michael Felderhoff, who comes from the Max-Planck-Institut. I'm not going to read this in German, from the Max-Planck-Institut for Core Research in Germany. And he's coming to the webinar to discuss the challenges we faced during the duration of IMPACTIVE to scale up mechanochemical transformations from the lab scale to a bigger scale that may work in industry, like the kilogram scale, which comes with a different series of challenges compared to traditional chemistry, because of course you need bigger ball mills, you need bigger structures to make the mashing process efficient. Michael is a research group leader at the German Max-Planck-Institut for Core Research, and his research focuses on material development and energy for hydrogen storage, among other things. And he also works on mechanochemistry to try to make synthesis of different types of molecules greener, and has been a member of the IMPACTIVE project since the very beginning, working on scale-up. And also, as a little bit of a surprise addition at the end of the webinar, we will also have Jan Schöbel, who's a postdoctoral research scientist working with Michael. at Max Planck. And Jan began his career as a PhD in organic chemistry in Aachen. And now he's working also in the scale up of mechanochemical synthesis. So it's a pleasure to have you both. We'll first hear from Professor Felderhoff, who will do a presentation about the different challenges we faced in IMPACTIVE and the problems of scaling up mechanochemistry, hopefully some solutions as well, not only problems. And then at the end, we'll have a Q&A with Michael, Jan, and myself moderating. If you have any questions for that session of Q&A at the end of the talk, please use I think the YouTube chat to address them, and then we'll be reading them at the end of the session and passing them on to both our IMPACTIVE researchers. Again, last mention, just in case I forgot, IMPACTIVE is a project that got funded by the European Union through the Horizon Europe program. It's a pleasure to be part of this project. And without further ado, Michael, please, the floor is yours.
Yeah, thank you very much for the introduction, and welcome everybody to this IMPACTIVE webinar. You see the title of my presentation, Ball Mills for Mechanochemical Reactions, Challenges in Scaling Up. This is what I like to present today, and what I like to do is to show you some general things about what people do if they work on mechanochemistry. Normally, the people working on mechanochemistry, or most of the people working on mechanochemistry, use systems you find here on this side of the slide, on the left side. These are the typical planetary ball mills with different sizes, or also shaker mills like these ones here. But the problem with these mills is that they are limited in the amount of material you can produce during the milling process. And if you have developed an interesting mechanochemical synthesis, then you must also think about how can you upscale these kind of processes, or how can you upscale your synthesis. And this is what normally the people are not doing, is that they have or they have not the right equipment available. You must use different types of, or can use different type of ball mills with different sizes. And at the end, you like to do it in a size, in an amount that you can also think about industrial production processes. Please let me know that, of course, if we develop in industrial processes, or scale up our systems, we must also think about the money what we have to spend for all this kind of chemicals what we need there for the upscaling process. So this is one very important factor which should be also taken into account. What can we do, and how much money do we have available for the upscaling process? So what we have used in the last months, also during the IMPACTIVE process or program, is different types of mills. This is this kind of a Twitter mill, this kind of drum mill, and this kind of eccentric vibration mill. All these mills have different advantages and different disadvantages. We tried all these different mills in our process for the synthesis of co-crystals during the IMPACTIVE program, and I like to show you results, some difficulties, and also some positive results of these kind of experiments. So let me give you a short introduction why we think about co-crystal synthesis on a lab, going from a lab scale to a more closer industrial scale or kilogram scale. So in general, we know from a huge amount of APIs are known that they have different types of co-crystals, and these co-crystals could have interesting additional properties compared to the pure API. For example, with the ibuprofen, this is the problem with the ibuprofen is that the solubility is bad, and it would be great to increase the solubility of the material, because then you can also increase the analgesic effect by with this kind of co-crystal formation. And nicotinamide is a well-known material, and also the co-crystal is well known from the literature. So that means the general structures and properties of the materials are described. Yeah. And once again, it is also known that you can produce co-crystals of these materials from solution-based synthesis. But these solution-based synthesis have some disadvantages. First of all, it requires large volume of solvents. These processes are energy-intensive processes because you have to cool and heat up. And they also these are time-consuming methods because sometimes you have slow evaporation and or slow crystallization, and these things can be very time-consuming. So, and this is also the topic of the IMPACTIVE project. Develop more energy efficient and eco-friendly approaches by mechanochemistry. And as I mentioned before, we use as a standard procedure to get some experience with these different types of ball mills with this kind of ibuprofen, because we have got a huge amount of ibuprofen from the BASF company to do also experiments on a kilogram scale, and that was very important for the whole process and the developments. So upscaling, co-crystal upscaling, ibuprofen, nicotinamide, all these, we have used all these 3 different ball mills. We prepared an amount of 2.6 kilogram with this eccentric vibration mill. We prepared more than 3 kilograms with this drum mill, and we also used a Twitter for sequential batch processing for the synthesis of roughly half a kilogram of these co-crystals. All this work is published, and you can find, if you are interested, these you'll find more information in the publications here. So let's start with the eccentric vibration mill. I think that this is a very interesting type of ball milling process, because this is not very common in labs, and this are normally only used in production processes or for the demonstration of upscaling processes. This type of mill was developed in the 80s and the 90s of the last century from Professor Gock. He worked at the University Clausthal-Zellerfeld in Germany, and you see here a scheme how this ball mill looks, or this eccentric vibration mill looks like. So this is a grinding pipe. This is the drive. This is an unbalanced drive, and on the other side you have a balanced mass. And here inside, and this is important to see and important to mention, you see a huge amount of balls inside this eccentric vibration mill, and the normal filling rate only with balls of this vibration mill is roughly 80%. So that, and the rest, the free volume between the balls is the free volume for the mixing materials. And you can combine these types of mills with several modules together, so that you get a much bigger system for a higher production rate. So I like to show you how this mill works with a short video. And you see, this is the drive. Now we see a slow motion, and the real-time processes is, maybe I can do it once again. You see, it's very fast, but important is that the range of movement of this mill is very low. And this means that also the overall energy consumption of this mill is very low. And how this looks like inside can I show you with this video. You see once again this high filling rate with balls, and this is a slow motion, how the balls are moving, how is the movement of the balls during the milling. Yeah. You see that you have this kind of movement of the balls, and yeah, the balls have it is a big difference to a normal mill, what we know from shaker mills, or that we have a very long distance for the ball movement. But at the end, I can mention this is a very efficient mill, and I also like to mention that I've got these videos from the company who's producing these meals, that is Siebtechnik, Thema. And we are lucky that this company is very close to our institute, also in the city of Mülheim an der Ruhr. And how it looks like, if you want to do real industrial processes, that is shown here. This is a eccentric vibration mill for industrial processes. And, and I visited the company last week, and I've seen such a big mill, what they have produced, not for mechanochemical synthesis, I must say this. It is produced. This mill was produced for the food industry, but the impressive numbers which I've learned are that you can have up to 1 ton of material per hour produced or used or processed in this kind of mill, and this can be done also in a continuous process. So that means if you do this for 24 hours, you can produce in the best way 24 tons of materials with only one of these mills. Nevertheless, what you have different options. You can use special kind of steels. You can use different inlets. You can use ceramics, elastomers. You can use bolts or rods. You can heat it. You can cool it. You have a noise protection housing, and you can also do it in a batch or in a continuous way, as I mentioned before. And you can use it under inlet or gas conditions, or also under vacuum. So a real industrial mill which can be used for the production of or for the synthesis of mechanochemical processes. So let's see what we have done with this kind of mill. We used two different mills from this company, from these eccentric ball mills. One with a milling media of stainless steel, and the other was aluminum oxide. And the inlet was also made of aluminum oxide. So the overall volume of this mill was a little bit lower. Therefore, we could also only use a little bit lower amount of materials. And what we used here, with the stainless steel system, 2.8 kilograms of the mixture of 1-to-1 mixture of ibuprofen and nicotinamide, and we got a recovery of 94% in this way, and here of 81% in this way. Let me say that this is not optimized, and I'm be sure that we can get a recovery of more than 95% with these mills, also after the milling process. Okay, this is a result, but how does it look like during the milling process? And therefore, we sampled, we took several samples during the milling process. We did X-ray diffraction and also DSC measurements. Here you see the nicotinamide and the ibuprofen, and the important reflection is this at roughly 2 degree 2 theta. And you see in both cases, if you use steel or aluminum oxide after 50 minutes, this the main reflection is, yeah, comes from the produced nicotinamide. But you see also this very tiny reflection, which is a residue of ibuprofen. And this is still there, which means that the process is not finished. You can see also this after after 60 minutes with the steel in the steel or with the steel grinding media, but after 120 minutes everything's gone. This is a little bit different with the aluminum oxide because the aluminum oxide, the impact of the aluminum oxide is a little bit less, meaning that we need a little bit longer time for a complete conversion. And at the end, we need roughly 150 minutes with aluminum oxide milling media, but then we also have a complete conversion and we don't see any kind of reflections from the educts anymore. And the same can be observed in the DSC measurements, what you can see here. After 120 minutes, the only melting point what you observe is the melting point of the co-crystal. So you see this works very well and without any problems, and you get also the material out of the milling machine in a very simple way. What we also have to take into account always is the question of what happened during the milling and how clean are our materials. What's about impurities, and what's especially about impurities regarding abrasion from the milling process. And this is also a question what we try to answer with these kind of developments. We measured the impurities in the pure samples, aluminum, chromium, iron, and nickel. And you see that also in the pure samples, in the ibuprofen and the nicotinamide, you find a little bit of some ppm of this different type of metals. And at the end, you see what we observe with aluminum oxide inlet and the milling media from aluminum oxide. More or less no increasing of chromium. That is of course understandable. We have a little bit increase of the iron and also no increase of the nickel. This is a little bit different with stainless steel equipment. Aluminum is increasing, also the chromium is a little bit increasing from the steel what we use for the milling process. Iron is a little bit higher, and also nickel is a little bit higher compared to the educts. But we have also done a calculation what is the daily dose of the amount of nickel what you can, if you take an amount, if you assume that the co-crystal daily dose is roughly 2,400 milligram for and this means if you calculate the overall amount of nickel, for example, this is below the maximum permitted daily dose, which is pre-described by the ICH guidelines. So in principle, that is a good information. It is not a problem to use aluminum oxide ball milling equipment. It is also not a big problem to use iron-based ball milling materials for the synthesis of these for these kind of co-crystals. So this works very well. That was very nice to see these kind of results. Let's move to another mill. Let's move to the Simuloyer. And the question is, how does a Simuloyer works? Also, if you haven't seen a Simuloyer in reality, this is a completely different story compared to the eccentric vibration mill. The Simuloyer is a high energy ball mill, a very high energy ball mill, and you have very high accelerated balls inside. You see this video here. This is also a slow motion. Otherwise, you couldn't see anything from the moving balls inside the ball mill. And how does it work? You have a shaft which is rotating, and you have a rotation number of up to 1,500 RPMs. And what you also need, or what is also different, you use very small balls, and this is very important. you want to have a high impact with these small balls and with this kind of ball mill. And if you use very small balls, the area for the energy impact is much smaller compared to bigger balls, because if two balls hit together, you have a deformation. You see a deformation, and during the deformation, the area is increased, and that means that the input of the energy during the ball milling is much higher compared to much smaller balls. So that is the reason why the people use very small balls for this kind of milling equipment. And this is in general, I can mention this in general a batch process, but for industrial processes, you can get milling equipment with a volume of up to 900 liter, so that you have very big vials and you can produce several hundred kilograms in one batch process. So what we have done with our milling equipment, we have only a small milling equipment with 1 and with a 2-liter batch milling vial. And we also did the same experiment with the ibuprofen, and we did 8 fillings. We did 8 runs, 8 fillings without cleaning. So we want to see, can we do a semi-continuous process for the ibuprofen nicotinamide co-crystal synthesis? You see some other important numbers. What you see here now are the results of this process, of one milling process. Once again, DSC measurement and X-ray diffraction. And what is interesting to see, that only after 10 minutes, most of the co-crystal is formed, and we have only a very small amount of ibuprofen left. Yeah, you see here this very tiny reflection. And after 20 minutes, the whole process is done. So that means that this energy, this mill has a very high energy impact and a very high conversion rate in a very short time. Nevertheless, once again, the question is, what's about the abrasion? Is it a big problem doing these mills with these mills? And I can mention, no, it is still not a problem. And we have done from every batch our the measurements of different metal impurities, and you see that there is no additive of or addition of impurities in the different batches. Sometimes we have higher amounts, sometimes we have lower amounts. This is a question of where you have taken the samples from for these kind of measurements, from which place you have taken it. So this is also a very nice result. Nevertheless, we will see it at the end. For longer milling time, and because of the high impact, you can expect, and also depending on the type of material you have inside your inside your simuloyer mill, you can expect a higher amount of impurities during the milling. Let's go to the next option. Let's move to industrial drum mills. These are the biggest drum mills you can get for any kind of processes, and they can be very big. For example, for ore processing, for example, like this one, this has a diameter of 8 meter, and you can mill hundreds of tons or thousands of tons per day with these kind of drum mills. Nevertheless, maybe people who don't know this or the other have seen this, you have different conditions for the drum mills. First of all, and this depends on the rotation number of your drum. You have first of all, you have a cascading process where the balls fall down, but are moving around depending on, as I mentioned, on the rotation number. And the more interesting is the impact process, where with increasing rotation number the balls are are pushed to the top of the mill and fall down, and with this falling down process, we have an impact on our material from during the milling. And you can imagine that this depends, of course, from the diameter and from the size of the balls and from the size of the milling wire of the drum mill. So, but before I show you the results, what we have done, I like to show you what can be done with very big mills. This is a presentation I've got from Dean Morrow, and for more information you can contact Dean Morrow. And they used also a drum mill for an industrial scale mechanochemical destruction of PFAS. So for polyfluorinated aryl and alkyl compounds. And you know that these kind of materials are some so-called forever chemicals which are not destroyed in the nature. What they use, and you get an impression here, the size of the mill they use for this kind of deconstruction. They used a Marcy mill with a volume of 1,700 liter. I only want to show you that this works also with very high volumes, and maybe this is an interesting option for people working on the recycling of plastics. This could be, yeah, because plastics are, we have a huge amount of plastics waste, and we should also think about how we can do the deconstruction or can use this kind of milling with very big ball mills. Yeah, and they also put a lot of different additives to this process to destroy this fluorinated compounds, and the most important component was potassium hydroxide, and at the end they produce potassium fluoride, as you can imagine. The other additives were important for the general processing of the whole milling process. So, but let's move once again back to our results with mechanochemical synthesis in a drum mill. We use this kind of drum mill, which was delivered from the Reg company, and we also try to do the ball milling and to do the co-crystallization with ibuprofen nicotinamide. So what you see here is what happened during the milling. So that was surprising. If you stop the milling after some time and you open your milling vial, you see a change in the reaction mixture morphology. So first of all, after 30 minutes, you have a fine powder. After 60 minutes, you observe a hard solid on the walls. And after 120 minutes, you have no powder anymore, you have a hard solid on the walls. And you see, we started with small balls in the beginning. And after we have observed this, we added some bigger balls here. Yeah, and you also see that after roughly 390 minutes, we still have a hard solid at the walls with the smaller and with the bigger balls. And you see here also the conversion rate. First of all, depending on the milling time, we have the conversion rates increases. And here we added a little bit. Here we added an additional amount of small balls. Here we added an additional amount of bigger balls, and in all cases we have an increasing of our conversion rate, but it stops at a rate of roughly 85%. And then you all know, all the people know working in mechanochemistry what you can do then. You can also try a lac for better milling process conditions. And we added here some ethanol as a lac. And we started once again with the ball milling, and you see after we have added the lac, after a very short time, we came up with a very close to 100% conversion of our material. And what we have done then is that we added the luck in a next try from the beginning on, and after a very short time, after roughly 1.5 hours, we have a 100% conversion of the material. And what we get at the end is we have ethanol evaporation over the night. We have simple sieving of the grinding media, and we get 99% of our material back from this milling process. So at the end, this also works very well. Also, we had some problems in the beginning with the right size of the milling balls, and we also came up with the idea to add some luck to the material. The same what we have seen before. I skipped this now. What I also like to mention here is we have the same we did the same measurements about metal impurities, and we observed once again no really increase of metal impurities during the ball milling from abrasion. So let's go to one other example: motivation for production of paracetamol. Why? Paracetamol is also very, very important as API, but it has one disadvantage. The disadvantage is that it exists in two different polymorphic forms, and the most stable polymorphic form is this one. And you see it has a little bit a herringbone structure, and this makes it very difficult for tableting. The more interesting form would be the form 2 for tableting, but this is only a metastable form, and this could change very easily from this form to the more stable form. And therefore, with co-crystallization, you can produce different types of co-crystals with paracetamol to get better tableting, for example. Yeah? And we choose at the end for our experiments oxalic acid, because this is also a material which can be used without any problems as an additive for APIs. So what have we done? We started, of course, with small amounts in planetary ball mills, and we can do this with planetary ball mills up to a volume of 500 milliliter, and we had inside an amount of roughly 25 gram of paracetamol. And after some time, we had got a complete conversion without any problems. By the way, you can get these results are recently published here in this paper, Organic Process Research and Development. So, and if you can do this, of course, to think about upscaling and that you can try also higher amounts. And we did it with 250 grams, once again, a drum mill, and with a 5-liter vessel and 150 gram oxalic acid. So this is a 1-to-1 mixture once again. Here are some other, and we use once again very small 1 centimeter balls. And what we observe, the similar results what we have seen before with the ibuprofen. After 30 minutes, we started with the hard solid at the walls. You must sizzle this down with a hammer and a sizzle, and after 60 minutes, it's the same process or the same problem anymore. And after 90 minutes, once again, always if you use this small balls, you don't have a powder anymore. You have a hard solid on the walls. So what you think, what you can do afterwards, of course, this is what we have done before. We add a lag to our materials, and we use once again ethanol because it's very often used in pharmaceutical processes. So, and that was a little bit surprising to us. What we observed then after 30 minutes becomes a little bit different. The overall system, it changes a little bit the color, yeah, and we added a little bit more lag, but at the end, I must say, we end up after some milling time with a yellow paste and with a characteristic bad smell. Please let me mention that before we did this, of course, we have done this process, the addition of lac, on a small scale to see, is it possible to do and to get a complete conversion with this kind of luck of ethanol as luck in a ball milling process. And we were very surprised to see that this is different with this in a big with these materials in a big scale. And at the end we came up, and I think it's not really difficult to understand that we have esterification because we have oxalic acid inside, we have ethanol inside, and we produce the mono and the diester of the oxalic acid. And that is the reason for the bad smell and for the process what we have observed. So, but once again, this was not observed on a small scale, and that was very surprising to us. So what can we do in addition to that? Of course, we change once again. First of all, we have seen that we get the hard solid. We did another experiment with bigger balls. Once again with a diameter of 3 centimeter, similar amounts of paracetamol. That works very well in principle, no hard solid anymore, but we had no complete conversion. And you see this if you check this reflection from the paracetamol, and this is still present also after very long milling time. So addition of another luck. Now we use not ethanol, we used ethyl acetate, also very often used in pharmaceuticals. And with this, it works very well and very easy and very fast. And at the end, we have got a complete conversion of our material. And after additional 60 minutes, the whole process was done. And let's show you the last experiment, what we have done with this kind of materials. The final experiment with a 14-liter vessel, an overall amount of 1 kilogram of paracetamol, 600 grams of oxalic acid, 80 milliliter of ethyl acetate of lac, and 15 kilograms of milling balls. And after 3 hours of milling, we end up with a complete conversion of the material to the co-crystal. So that's all of experiments I like to mention, I like to show. I have some general indications in addition to that, what I like to mention at the end. There are some general indications. First of all, what you can expect if you use different types of balls for industrial process. You can expect, but this is always depending on the materials, on the milling time, and on the machine, and increasing of abrasion, moving from drum mills to eccentric ball mills to simulators. And you can also expect an increasing of the energy consumption from the accelerator, from the eccentric vibration mill to the drum, over the drum mill to the simulator system. So the simulator is the highest, the mill with the highest energy input, but it also needs the highest amount of energy. Let me give you one additional information, which is also very important for APIs. If you start to do new developments for APIs, and this is what we have done in the IMPACTIVE project, because all new manufacturing process, you must monitor all the changes of your manufacturing process. And if you move from a solution process to a mechanochemical process, you have to detect and control any kind of contaminants. And one of these important general problems for APIs are nitrous amines. Where they could come from: first of all, supply chain stability, process oriented, and this can also always influence the amount of nitrous amines in your API. And because most of the APIs are amine compounds or secondary amine compounds, we must always think about if we develop processes on mechanochemical basis, that also nitrous amines can be produced, and it should be checked always what is the amount of these materials in your mechanochemical process. So let's summarize some things, what I've presented in, first of all, our studies have demonstrated the feasibility of different ball mills for upscaling mechanochemical cold crystal synthesis. We also use these drum mills in the IMPACTIVE project for the synthesis of other APIs, but all these processes are just in the in the state of the publication, and therefore I cannot present this today here in this seminar. We have shown that we can produce high purity co-crystals during neat milling or with different lux as grinding auxiliaries. We can get the material back, or we can use simple sieving the grinding material, and this results in recovery of up to 99% of the desired product. And this is very important. During the upscaling process, lux may interact with the compounds being ground. This is a phenomenon that is not always observable at small scales. So you should always have this in your mind and should think about what kind of additional reactions can happen with your lug you are adding to your materials. Yeah, and at the end, acknowledgement. Several people worked on this topic together with me, and mainly it was Jan-Hendrik, who is also present and can answer questions now. Dinesh did a master thesis on this topic, and other people from the group are listed here. I must say thank you, especially to BASF for the gift of the ibuprofen. And if someone is interested to do some experiments with ibuprofen, I have a huge amount of material left. I must say thank you to Siebtechnik to use the mills in for our experiments, and also to the Reg company. Thanks to IMPACTIVE. And at the end, I like to mention, someone is interested in upscaling processes and wants to try some things. I'm running a startup company dealing with upscaling of mechanochemical processes. And if you are interested in this kind of reactions, I would be happy to come in contact with you. Thank you very much for listening. And if there are questions, I'm happy, or we are happy to answer most of them.
Thank you so much for a very nice presentation and very thorough presentation. We do have some questions, but before we move on to those, please let me quickly welcome Jan to the call and the webinar. Hi, Jan. We'll direct some of the questions to you as well. So before we start, I just wanted to highlight a couple of things from IMPACTIVE. The first one is that you presented several examples of papers. All of the papers that have been published during the IMPACTIVE project through IMPACTIVE funding are going to be available, or are already available, in our Zenodo community in full open access. Even if they're protected in the editorials, you can find a free to read version in open access in our Zenodo profile. So please go to that. And then also, an important outcome from IMPACTIVE is going to be the mechanochemistry educational platform that was put together by the Communication Dissemination Work Package, and it's going to sort of gather a bunch of resources, including presentations, videos, webinars like this one, and also papers and training materials on mechanochemistry. So that's going to be a legacy to the European community for like funding this project. And things like this webinar are going to stay there forever. I encourage you to check that out as well. And yeah, without further ado, I'm just going to jump to the questions. If I find the right document, where I've been taking notes during the presentation and getting some of them from the audience. So the first stuff, I think you kind of touched on it a little bit, because you showed us that huge ball mill that was already available for very, very large industrial scales. But how are these ball milling techniques ready for reactions at larger scales, especially when you move into beyond the kilogram and you go to bigger scales, and you may need to consider things like safety, monitoring the pressure, monitoring the temperature, following the reaction. Either one of you, I'm happy to hear from you.
So let's give one example, and these are the Twitter mills or the simulators from the TOTS company. These systems are available since several years for production processes, really real production processes and mechanochemical reactions. Um, they sell. You can buy these kind of systems. I know in the past they were also used for very hard materials, and they mainly up to now mainly for inorganic compounds. And as I mentioned, the impact of these machines is very high, so that you can expect for organic materials a very short reaction time. And as I mentioned before, the size could be very big. Of the milling vial could be very big, and up to roughly 900 liter. And if you can imagine how many material you can mill inside such a big milling vial,
Mhm.
it is finished, or it's ready for production processes. And they have also a lot of additional components available for these kind of mills. As I mentioned, you can cool it. These systems are in general cooled because the high energy is producing a huge amount of heat, and you must reduce the heat during the milling process. So you can cool it, you
Mhm.
can heat it, whatever you like. You can measure the pressure inside, yeah, and you can run it under inert gas conditions. So all these are possible options.
Mhm. I'm gonna send the next one to Jan, just to have some insight from how you do research
Mhm.
in the lab. We got a question about the, because we saw a bunch of X-ray spectra during the presentation. How do you do those measurements? And do you manage to do them live, like while the reaction is happening in situ, or do you actually, stop for a bit, do the X-ray? How does it work? Because it looks like a very nice but also a little bit complex way of monitoring a reaction. It's not like following something with an NMR. How do you normally deal with it?
Yeah, so typically we are stopping the reaction, then opening the reactor and taking samples to measure XRD. And we have a department here at the MPI who can measure different analytics. We have also the possibility to do it in situ, but not for the large mills. So for the large mills, this is, as you can imagine, very difficult to develop a system which can really go through this big metal vessels and measure in situ something. So this is something which we can do on a small scale, but for the larger scale at the moment, we are just opening the reactor and looking what's inside. It's also crucial to see how the reaction mixture behaves. So especially on the larger scales, you can imagine it's a totally different story if you have some heat spots or some a bad mixing and you have very reactive reagents inside. So you actually want to stop them after a while and look if everything is fine. And at the moment, we can only do this by just opening the reactor.
Mhm. Sorry, is there any work done to monitor like life as well? Yeah, we could probably, is there any way of like doing this in situ, or is it too complicated?
I think it's quite complicated. I mean, I'm not saying it's impossible, but if you imagine you have a vessel which has a few centimeters of stainless steel, then you need to go through this with the beam
Mhm.
to measure the material. And I think that this is rather impossible at the moment. So you could imagine building machines with very thin walls and material where you can go
Mhm.
through with a beam. But then there's a question of how stable is this really? If you have 30 kilogram of balls and your material and everything is mixing with impact forces and so on, you have a very thin wall, then this is maybe something more of a safety concern.
Mhm. And actually, we got another question from the audience. I'm assuming it's someone who's like really interested in mechanochemistry, because they're asking about one of the mills you presented during the slides, the simulator. So they're asking, how much does it actually vary in terms of homogeneity and size, depending on where you put the sample and the product in the mill? Have you seen any differences? How do you get around that?
I think so. So if I get it right, the question is if there's like different conversion, for example, at different parts of the machine. because this, we have observed this. So sometimes you have some dead zones in the machine where you have accumulation of material, or you have this formation of hard solid crust, which at some points are more pronounced than at other points. So when we open the reactor, we always make sure that we take samples from different locations. But we have observed that there's really a difference in conversion. And sometimes what you also see, since the simuloyer has such a high energy input, it can be that you form your product on the surface, but below this is still some unreacted material, just because there's so much force. You're forcing your compounds to adhere at the reaction wall, and then you will just trap some of the starting materials beneath a product surface. So this is also something which we have observed, and where the right milling conditions are needed to really be able to get a good mixture.
So you can run these machines with up to 1,500 how's it called, Jan? RPM, yes. And we did it, and that is the reason why we have reduced during the co-crystallization. And I think that's also important for most of organic materials, reduce the RPMs during our experiments down to 800 RPMs. Yeah. And with this, you have a very good mixing, and you do not observe these kind of processes which were described from Jan.
There's always a balance of how much energy do you really need, how fast you want your reactions to be going, but also not to have these caking effects or to have any side reactions. So it's really a balance which need to be found out experimentally. For some reactions, it works great at 1,500 or even more, but for others, lower speeds are better. So.
We just got another question from the public. It looks like I'm making this up, but we're actually getting questions from the YouTube chat. They're asking about the tableting of paracetamol that I think you brought up at the end of your presentation. What scales are we talking about, and how can you tell the differences in stacking through X-rays? How exactly do you do that in the lab?
So we haven't done any kind of experiments about the tableting, because we choose these materials because this is well described in the literature, and it is well known how you can optimize these systems with co-crystallization. So we choose one of these experiment or these options or this materials to show that we can use these kind of bore milling processes also to get the right material. But we haven't done any kind of additional processes to check how good is the tableting of this material what we have produced.
I mean, there's a publication on that, so this has already been done before from Friedrich, who tested different co-formers together with different APIs, and then really pressed the tablets and measured a few characteristics of these tablets. So this is something which can be looked up online, but we did not retest it by ourselves.
Yeah, that's always something that comes up in terms of when you talk about mechanochemistry, about like how comparable are the pharmaceuticals you manufacture to the pharmaceuticals we already have. In terms of, like, obviously the chemical composition is the same, but are you going to have the same effect? How do you actually judge that before putting them in the market? I have a sort of a personal curiosity, and I mean, you've got BASF here in the last slide, because how I came into contact to mechanochemistry was actually before we created Agatha, before we joined IMPACTIVE. In my sort of previous life as a science writer, we did a feature on mechanochemistry, and it's been going on for a while. We've got a very nice blog post on the history of mechanochemistry on the IMPACTIVE webpage as well. It was already there a few years ago, and by that I mean like at the end of the
compared to classical solution phase approaches, often more sustainable and also more effective. And this is something which also companies and larger companies are recognizing, especially if we have these things going on like the European Green Deal, in which companies need to produce CO2 neutral by 2050. So companies need to find solutions to make their processes more environmentally friendly. And I think that mechanochemistry is one of the technologies which have been noticed or notified again to make this possible.
Michael, I don't know if you want to add something about the recovery of mechanochemistry as the the holy grail of sustainable
what I like
synthesis.
to mention, I don't think that mechanochemistry was recovered again in the last years. It was always there. Think about that. One of the main topics of mechanochemistry was the mechanical alloying over several not years, dozens of years. The mechanical alloying was very well known, but it was not transformed to the organic chemistry or to inorganic chemistry. But the mechanical alloying is a very old and a very common process for mechanochemists. Yeah,
I mean, same
so
for
I think
co-crystals, right? It's just
yes,
some
this
things have been
also this in
happening.
addition. Yes, but the to do also chemical process reactions under mechanochemical conditions. This is a thing what you normally not learn in your studies. What you learn is solution chemistry and not chemistry
It's
without any kind of solvents or something like that. And
it's
this is
funny
what
you
we
mentioned that because I think I only did one mechanochemical reaction in the lab back in the time, and it
yeah
took me forever to find someone who had a ball mill,
yeah
because
Maybe also
everybody had
one,
flasks.
maybe this is also one of the reasons why it maybe got less popular, because people just did not understand what was going on. So it was a long time that it was really a black box, and then there was the development of all these in situ measuring, and people could look more detailed into the reaction, to the mechanisms, and understood more what is really going on. And this is maybe something which also pushed the field a little bit more forward.
Mhm.
But I'm
Okay,
not sure
we've
about this.
got.
This is just a speculation. So
I was gonna say we've got another question from the public, but because of time, I'm gonna probably instruct that person to contact us on email because we've got plenty of ways of contacting Impactive through the webpage, our email. We've got the newsletter, we've got social media. So please send us that question. We can pass it on because I think we've been here for a while. But it's been really nice having you both. I don't know if you have any closing statements or any closing ideas that you want to definitely mention about scale up in mechanochemistry and maybe reflecting on the success of Impactive after almost 4 years of working together.
so over the Impactive project, I must say we all have learned a huge amount of new things. We experience a huge amount of new processes, and we have seen that the mechanochemical processes can be used also for the synthesis of APIs. What is really one thing what we do not understand completely, what is the best option for the upscaling process? It's not only ball milling, what we can use for upscaling. We have several other options for upscaling, but it's unclear, in my opinion, up to now, what is the best process for which kind of reaction. And unfortunately, up to now, this must be checked and tested. This is a thing what must be understand much more in the future to know and to get more ideas how we can discuss or how we can develop an upscaling process before we start with the experiments. And if we get some ideas about this, I would say this is very important for the future to get more understanding about the processes which are important for the upscaling, not only doing the ball milling, also doing the other processes what we can use, for
Mhm,
example, uh, uh, twin screw extrusion or something like that.
mhm. Any comments on that, Jan?
yeah, I would agree with Michael. So I think we are on a very good way to just bring this a little bit closer to industrial application. Of course, there's a lot to do, but since some of the mills are already present in industry, it's yes, or we can also see it as some kind of trying to repurpose these machines for chemical reactions. And as I said, I think we're on a good way, but still there's a lot which needs to investigate it, especially the kinds of machines and how these reactions behave under large scale conditions is something which is not well investigated. If we just take something like exothermic reactions, heat development, for example, this is typically not a huge issue on smaller scales, but with large scales, we really need to make sure that this can be performed safely. So I would think that in the next few years we will get a better understanding of these kind of processes and hopefully come even more closer to industrial.
I think it's a perfect closing idea, because I mean, Michael, you said about how we've progressed through IMPACTIVE, and then Jan, you focus on like the progress that remains to be done. So it's hopes for like a new project on mechanochemistry and scale up soon enough. It's been great to have you both. I just want to thank everybody for joining us on YouTube. Just remind everybody that this will stay online, so you can check it out later. If you've got any questions, please do reach out through our webpage, mechanochemistry.eu. It's an odd thing because the webpage mechanochemistry.eu will live on and stay as an educational platform on mechanochemistry, which is really cool. I need to thank the European Union and the European Commission for funding. And please stay tuned, because there's going to be another IMPACTIVE webinar coming up next month. So if you follow our social media and newsletters and webpage and all the different channels we manage here at the project, you'll get a notification and an email to join that webinar. Thanks again, Michael and Jan, for joining us today. It's been really cool to learn about your work at Max Planck and your work in IMPACTIVE. And I think that closes the webinar. Thanks again for joining, and hopefully see you soon in the next project meeting.
Okay, bye.